This is a BioVale anaerobic digestion SIG meeting, and it is on innovation to unlock growth in the AD industry. We know that there's a lot of innovation out there, so we thought we would do an event just focused on that. For those of you who don't know the special interest group, we've been going for about 5 years now, and we've got an amazing 475 members. So we put on events like this a couple of times a year. We also help members one-to-one. So if you want introductions, or if you're trying to get a project started and you need some support, then you can just get in touch. So one of the things we do is flag up opportunities in the region for the AD sector. And something I just wanted to flag up before we get started is the ADSI programme. This is funded support for the AD sector in the region. So if you're an SME in West Yorkshire or York or North Yorkshire, you could be eligible for up to £2,000 of funding. And that is funding in terms of support such as analytical assists or desk-based assists. So if you do think you might be eligible and you can benefit from this, please contact Anna Alessi. So we've got quite a busy programme to get through this morning. We've got quite a few talks, and what we're probably going to do is do the quick Q&A at the end. I'm just noticing in the web chat that somebody's saying that sound quality is really bad. I don't know whether I can use it. So I don't know if anybody's having real problems hearing, then just put it in the web chat again. I'm not sure what we can do so much about that, but anyway, we'll get on. I've tried to order the talk so that we go through in the order of the AD process. So we start with innovations around pre-treatments and we end up with innovations around digestate use. But we're going to kick off with an introduction by Jon Brigg from Stoic Options, who's going to set the scene as to why the AD industry needs innovation.
Okay, good to go. Excellent. Right, so so Jon Brigg, ex of Yorkshire Water, big asset base in the water sector, now independent advisor. We'll look at the asset base for AD. Water sector, around 40 million tonnes a year is treated in this process, but of course there's on farm, there's industrial applications as well. So the market here is significant, and there is a clear need for innovation to move things forward. And only in recent years has that started really moving and taking pace. So if you just click on to the next slide, please, Elspeth. That's gone too forward, so there you go, thank you. So that's not a Pac-Man in the top left, that's a nutshell. So in a nutshell, there is some legacy assets, the legacy need, historic need versus current need, and the world is changing. You probably all noticed this quite significantly, and it continues. So things like power supply and demand and the cost of that, fertilizer sourcing, focused regulation on things like carbon emissions. So the world is changing quite significantly, and there's demand here for an underutilized technology to be transformed. So what do we mean by innovation? An often misused term, so it's great just to get this established before a session like this. So there's incremental change, which is doing the same things differently, just incrementally getting better. And then there's doing things different, which is transformational, so that's doing different things. So the actual innovation is the implementation of that benefit. And I think what we'll come on to hear from these the panel of speakers here are some great options that can be implemented or researched and developed further to implement and therefore affect the change. So just historically, it's good to set the scene here, is AD, anaerobic digestion, was basically for stabilization purposes. It was there to reduce odor and to perhaps reduce volume. But really, when this was pushed forward in the 70s, 80s, and pretty into the early 90s, it was there simply to reduce odor. And there was no value recovery in essence, because energy costs were low, fertilizer was plentiful, no need to change. But that, as I've just mentioned earlier, is up for change. So if we can move forward again, please, Elspeth. So the current need, so the AD innovation agenda. So what does the sector need to do? What does the industry that can potentially adopt this technology and the supply chain that feeds into it need to look at? So if you look on the right-hand side there, resource recovery. So there is a plethora of opportunities here to recover resources utilizing this biological process, be that pre-treatment, be that actually in process, or be that onward processing of materials that are recovered from the process. So that does two things. First thing is it's revenue generation. That makes it more sustainable in terms of cost, but it also makes it investable. But it also provides a resilience to supply chain. The manufacture of materials coming out of this process are suitably manipulated, suitably controlled, starts to provide resilience for everything from processing chemicals for plastic manufacturers right the way through to cleaning products. Again, opportunities here are significant. The second area is in reduced capex. So greater efficiencies means lower cost, more throughput for the same asset base, and that makes it more investable. And the third one is net carbon benefit. So just utilizing the figures from the water sector, AD is currently, whilst it's a viable and fully implemented technology, is in the top 3 biggest emitting activities in a water company. So whilst it stabilizes and produces power or biogas that can be utilized, it is still a significant carbon emitter. And in context, in the water sector, let alone agriculture or industry, is that the plan to get to net zero by 2030 is still circa 500,000 tons of carbon dioxide equivalent short. So you put that in context of a big asset base that I mentioned earlier, the opportunity here is significant for all sectors. So in terms of outcomes, just to wrap up, so what the agenda seeks to deliver, subsidy free. So can this, by generating revenue, by reducing capex, make this support free from the UK taxpayer? That's got to be an aim. Highly investable. So at the moment, investment is available, and that is becoming more prevalent. But by highly investable, I mean mainstream investment. So it's de-risked and highly significantly profitable, and therefore investable from a mainstream source of funding. As I mentioned, product manufacture. So the onward resilience of supply chains, less dependency on fossil fuels is a key area. And then no dependency risks. So the use of the digestate in agriculture is under pressure, significant pressure, for example. That's one dependency. So how does that dependency become reduced or mitigated by innovation? And then the last one there is process resilience. So how a biological process susceptible to feedstock change. So by understanding the process and controlling the process in much greater efficiency, much greater understanding, how is that then made more resilient to shock and not less productive? So hopefully that sets the scene for you. There is a significant market here, and I think what we're going to see in the next couple of hours is some really good examples of deployable understanding and knowledge. So with that, Elspeth, I'll hand back to you, and hopefully just saved a bit of time there.
Lovely, thank you very much, John. And the thing you were talking about with the dependency risks from the digestate, that was what our last AD event focused on, and it really is a pressing issue, I think. So thank you very much, and we will now move on to the next speaker. So this is Laura Stone from Econward Tech. Laura, do you want to unmute yourself?
Thank you. Yeah, for some reason it only lets the host unmute me. So, hi everyone. My name is Laura Stone. I work for the business development team at Econward Tech. Econward Tech is a Spanish technology company that has developed a technology to optimize the AD process from high solid organic waste streams, mainly food waste and source separated organics. The technology is based on a thermal hydrolysis system for these high solid organic waste streams. So next slide. please. Yeah, so just a quick run through of what I'm going to go through in the presentation today. Just hydrolysis is an already proven solution for organics. It's been going on in the wastewater treatment industry for years now. And we'll look at Econward's patented technology, which is a Biomark, that's its trademark name. And it's a pre-treatment for the AD process. And we'll focus on its application for food waste and source separated organics, which seems the most relevant nowadays, considering the new environmental bill that's being passed and how local authorities are going to have to comply with their source separated collection. And then we'll go through the high level research and results of the technology up until now and conclusions. So next slide, please. So what is thermohydrolysis? It's essentially applying pressure and heat through saturated steam to break down the biodegradable fraction of the waste. Thermohydrolysis is already a proven concept in the wastewater treatment industry. It's been a pre-treatment in AD for over 25 years now, when treating sewage sludge and these waste streams with low total solid content, so below 20%, generally between below 8 and 10%. And the results have been undeniably positive in this industry. It's increased biomethane potential, increased the biogas production overall, and it produces a substrate that is pathogen-free, and it's much more ideal for the AD process. Now, the challenge is bringing that same concept to high solid waste streams. Waste streams such as food waste and source separated organics, or MSW, are very heterogeneous. They're abrasive, they're corrosive, and that makes them a complex material to treat in the AD process because it's unpredictable, it can cause instability, and what we're trying to bring here is a solution to this challenge to achieve these same results that have been achieved in the wastewater treatment industry. So increased biomethane potential in biogas production and creating a hygienized pathogen-free substrate that is much more ideal for the digesters. So next slide, please. Yeah. So this is the Biomark. This is what we say is the solution to the challenge. The Biomark is designed as a pre-treatment for food waste or source separated organics, and it is a semi-continuous autoclaved process. And here in the semi-continuity is where the innovation relies. There's other thermohydrolysis systems out there, but they're all batch systems, and batch means high OPEX, very high OPEX. So the semi-continuity is what allows the Biomark to offer a considerably lower operational expense. And it's also designed to withstand all these abrasive and corrosive characteristics of the material that we were mentioning earlier, which is something these traditional systems, these batch systems, have had many issues with because it's caused the mechanical issues mostly, right? So just a few features about the Biomark. It can treat about 65,000 tons per year, and its only two limitations are particle size. So the feedstock has to be lowered below 30 centimeters, which is still quite a considerable particle size. And total solid content in the waste stream has to be between 20% to 80%, which is also quite a big range. It operates at 4 bar pressure, 150 degrees Celsius, and residence time is 20 minutes. And the type of feedstock it can treat is, like we said before, as long as it complies with those limitations, anything that has above 50% organics. So food waste, green waste, residuals such as fines containing over 50% organics, and other materials such as compostables or biodegradables. And I want to focus on these last ones a bit more because this is a type of material that we're getting more and more each time, these compostable paper cups and plates and napkins and so on. And they're not as biodegradable as their name makes them sound. So it's causing certain problems for the AD processes that are receiving more and more of this material each time. So the thermohydrolysis and the Biomark in general can create real added value with these types of materials, for example. And what you get when you process these feedstocks to the Biomark is a biomass which is homogeneous, it's chemically degraded. At the end of the day, what we're doing is we're taking the hydrolysis phase out of the digester and we're carrying it out effectively in 20 minutes. And then you get that substrate which is hygienized, pathogen-free, and much more suitable and ideal for the AD process. Next slide, please. And just a quick overview of research and results up until now. We've gone through different scales of testing with the Biomark, from lab scale to full industrial operation for the last 10 years. For the last 2 years, we've been operating our industrial scale reference in Madrid, where we've been treating Madrid City Council's source separated collection, and it has a 77% of organic matter in it. So even though it's source separated organics, we're not very good at it, as you can tell, because it still has a lot of pollutants in it. So hopefully you guys will be better at this. But we still managed to achieve a biomass for the AD, which was 98% plus organics. So if you look at the pictures at the bottom, that bottom left photo is how the material, the waste arrives at our facility. It's only gone through a bag opener. So that's really just as it comes, and that's processed through the Biomark. And what you get is that raw biomass in that third middle picture, where you can see that the organics have blended in all together, but it's not separation equipment. So you can still see all the plastics and cans and bits of textile and so on. But the difference is now it is a lot easier to separate. That raw biomass, when processed through standard separation equipment, like the packagers, sedimentation tanks, that you can find out there in the market, it considerably increases their efficiency, their separation efficiency. You can see on the last picture, it makes it a lot easier to separate all those light residuals like the cans, the plastics, the textiles, and so on. And that's how we're able to keep a substrate, a biomass, which is 98% plus organics, without losing organics in the way, which is also absolutely key. So next slide, please. And just, oops. So as a summary of the results that we've achieved in this industrial scale operation that we've been carrying out for the last 2 years, we've seen increases in specific biogas production between 30 to 50%, more biogas per ton of waste, a better quality biogas, 5 to 10% more methane content in the biogas, as well as reduction in the pollutants like H2S, so on, and increased treatment capacity for the facility because we're able to operate at lower hydraulic retention times. So that's on average 20 to 40% more capacity. The greater mechanical separation efficiency that we were mentioning earlier with minimal organic loss, very high degradation rates, 80 and 90% on COD and volatile solids, and a higher quality digestate, which is hydrogenized and easier for land application. And all these together translate into higher revenues from the increased capacity and the increased energy production for the facility, right? So last slide, please. So just that, to some of the conclusions, right? The Biomark allows 80 facilities to optimize the operation, especially for those currently treating food waste or similar type feedstocks, because of more biogas, better biogas, and all the other process improvements that add up to that optimization. It increases their treatment capacity due to the higher organic loading rates or lower hydraulic retention times at which it can operate. And then personally, for me, one of the most key impacts is it opens up a new feedstock for 80 operators, which are currently treating different types of waste streams and are probably not considering this type of source separated organics, like we said before, due to the complexity of the material. But it allows these facilities to integrate this new feedstock, guaranteeing stability of the process. So we're currently developing a couple of R&D projects on co-digestion with different feedstocks, and the results up until now have been very positive. So, and then last but not least, it helps comply with regulation. The Biomark, integrating a Biomark into an 80 facility can reduce up to 40% the GHG emissions of that facility, just against the same facility without it. And then it helps achieve organic recycling rates to meet with established targets. So next slide and last slide. Just the idea that I want you to stick with is that the Biomark is an innovative solution to optimize the AD operations, both technically and financially, and promote growth in the industry. So thank you very much.
Thank you, Laura. We're a little bit ahead of time at the moment, so we've got a question. I thought it might be good if you could answer it straight away. Is there a pumping limitation when operating with higher TS content?
There Yeah, there is. So it's really going to depend on the incoming feedstock. When we get very, very clean food waste, which has a much lower tall-side content, obviously you get a slurry, which is much more pumpable. So I wouldn't be able to tell you exactly where that that threshold is for the pumpability of the material, but yeah, I can get back to you on that exact number if you want.
But another question, which will be the last one before we go on to the next talk. What is the energy demand of biomass technology electricity?
Electricity.
Biomass technology, sorry, electricity to heat. And
yeah,
how does it compare to the extra biogas production?
I can tell you exactly that. Well, heat is obviously the main driver for the OPEX in the Biomark. Electricity consumption is very, very low. We're talking about 0.4 kilowatt hour per ton. And when it comes to heat, it's around 170 kilowatt hour per ton. So considerably higher. And then when you compare that against to the extra biogas production, again, it's really going to depend on the feedstock, because and on whether you're able to increase the treatment capacity of the AD facility. You'll get much more biogas out of operations where the Biomark enables for that increased treatment capacity, as well as that increase in the specific biogas and specific biogas production and the methane content in the biogas flow. But yeah, in general terms, I think with those two numbers, you can kind of do your own calculation on what the ratio is.
Okay, lovely. Thank you very much. We've got some more questions, but I think we'll move on to the next talk now.
Sure.
And we've got a double act for the next presentation. Raising yields with probiotics, Matt Smith from NCH and Chris Hoare from Amur.
Well, good morning, everybody. Thanks for giving us this opportunity. So I'll just introduce them all very quickly, and then Matt can just introduce NCH. But basically, Amur is the AD division of AB Agri, and AB Agri is the agricultural division of Associated British Foods. So that's British Sugar, Twinings Tea, and Pie Market. And AB Agri is predominantly a feed business, and what we spent years on is looking at how we can bring solutions to farmers to increase the efficiency of meat and milk production. And the way that we've approached AD is very much in the same angles, is to look at what can we do, not mechanically, but what can we do to try and increase and make more efficient the AD process. And so we have a lab in York, and we also have an AD plant in Yorkshire, a gas to grid AD plant. And the reason that we have the AD plant in Yorkshire is A, to make money for the group, but also it's so that we can commercially test things that we've tested in the lab. And so a lot of things, new ideas we've looked at in the lab, if they look like they've got anything that commercially could stack up, we then try it in the AD plant. And one of the things that we've done is the AD Pro, and that's very simply probiotics for AD. Next slide, please. So the easiest way to try and describe AD Pro, it's a bit like Yakult, you know, those yogurts that you get that have got really good bugs in them to make generally the bugs in your stomach work a lot better. And so that's exactly what AD Pro is doing, is it's stimulating and turbocharging the good bugs within the first step of the AD process, the hydrolysis step. And again, what we've tried to do is to try and make how we apply it relatively simple and easy to operate. So, you know, you can put a bit of the kit that goes in. Matt will explain a bit in a minute about it, but it's all really simple to operate and really simple to install. So Matt, we've partnered with NCH. Matt will just introduce NCH and then talk about the dosing equipment and how it works. Over to you, Matt.
Good morning, everyone. My name is Matthew Smith. I'm the sales manager for NCH ChemAqua. NCH is a global company based out of Dallas, Texas, and ChemAqua is the industrial water treatment arm of that business. We specialise in industrial water treatment, steam, cooling, and effluent treatment. And the technology that we've got, our AD Pro, comes from originally from our effluent treatment offering. So we used to specialise in our Biomark system, which was an aerobic treatment for reducing fat cells and grease and suspended solids in effluent streams. And we realised that there was potential for this equipment to work in AD to help with the hydrolysis process by applying bacteria in a very conservative way, controlled way, to be able to improve the process. So yeah, if you could go on to the next slide, please. So when we're talking about it, we're talking about AD Pro, and it's a two-stage process, and essentially it consists of the biological application, biological treatment, the spores, and then the EcoCharger unit. So as you can see, that's an example of our EcoCharger unit. That's our version 2 unit. It's a very small unit, approximately 50 centimeters by 60 centimeters, and it's scalable on the AD process based on size. So a small sort of 1 megawatt plant would require 1 unit, up to a 5 megawatt plant, which would require 3 units. And what we're doing with the unit is we are taking the spores and we are reactivating them on site, and I'll talk a little bit more about that later. But we reactivate them on site and inject them into the feedstock as it's fed into the digester. And we've been lucky enough through lockdown, Amur, working with those guys, we've managed to trial this for quite an extended period on the plant at York. And I know Chris is going to talk you through some of the results that we've had from that trial.
Okay, so next slide, please.
Slide.
Thanks, Matt. So what we've, again, trying to monitor anything in AD is always challenging because of the ups and downs of the process, but the logical thing we took was to try and compare sort of a period of the same time, 1 year versus the following year. And the other thing is that because we'd only done the work in the lab, actually upscaling it, we had to feel our way as to how much we actually needed to do in terms of the amount of units and the amount of product we put in. So this graph basically shows a timeline. You've got the orange line at the top is basically the target that we set above the grey line, and the grey line is our sort of normal level of production. What we set ourselves to achieve was that we wanted to see at least a 10% increase in biogas production, because if you get down to 5% or 4%, it's really difficult to actually to show that and make it stand out commercially for people to commit to it. So the squiggly line is the daily gas production, and the dotted blue line is the sort of average of those spikes. So the first thing we did was, when we started comparing year against year, the first thing we did is that we put 1 unit in, and we did get a bit of an uplift in biogas, but it wasn't the sort of 10% plus that we wanted to see. So what happened was we then put in 2 units, and it was absolutely great. You know, we could see that the biogas, which is the second section, we could see that the biogas production was increasing. And then what happened was that we had some problems with one of the units, and in actual fact, we went back down to 1 unit. And what was interesting is that we saw, as soon as that other unit came off, we actually saw that the biogas production started to dip. So we actually could see that, number one, if we had 2 units, we saw a real positive effect. If we had 1 unit, there wasn't quite enough going in to make a significant difference. And then you can actually see that we, in the very last quarter of the slide, we had some problems with Fostak, etc. But then we got the 2 units going back up again, and it recovered back to the sort of target that we were looking to achieve. So literally for us, by simply just adding these probiotics, we've seen an uplift in our production of biogas. And the good thing here is that it doesn't matter whether or not this is food waste or whether or not it's crop based. It can be used by any AD plant. And again, if you go on to the next slide, then the next slide, again, I'm very conscious of of the time that we've got here, but I think the easiest thing is to drop down to the bottom, which is that what we did is that again we tried to break this down into comparing normal running conditions versus just taking the good things. So in other words, if we started looking at the normal period, when you look at everything year on year, where you have to shut the plant because you're doing carbon changes, all sorts of things that cause problems, we actually saw an uplift in biogas of 7.2%. If we then actually compared the same time periods year on year and actually just took out all the bad events, so just looking at normal good running times, no problems in the plant at all, we saw an uplift in biogas of 14.2%. So we're pretty confident overall that we should see at least a 10% uplift in biogas. So if you go on to the next slide, please. This literally just graphs exactly what I've been saying again, which is comparing the normal running versus, as I said to you, when we look at absolutely everything and all the problems we've had versus just looking at the good running days, and you can see overall that there is a significant gain overall in terms of the feedstocks that we feed at our AD plant. They are predominantly food wastes that are processed and then made into a soup, but there's in terms of the agri plants, then we see no reason why this product won't perform as well, if not better, in agri plants. And we've actually got some commercial trials with some of the customers that we deal with in agri plants that are just beginning to start, and therefore we'll have even more data from those most likely within about 6 to 8 weeks time. So next slide, please. So I'll just hand over to Matt again, just to cover off a bit more.
Yeah, so I'll just sort of talk through what the technology is and just give you an introduction to how it works. So AD Pro additive, it's produced off-site under laboratory conditions. So at the moment, we're actually growing the bacteria in our lab in the US. We then deactivate the bacteria, we form spores, and we bottle up the bacteria and then ship it over to the UK. We're actually in the process at this moment in time of changing production to our European facility. Part of the process of change is we have to look at our quality control, and the AD Pro additive is subjected to rigorous quality control tests. So each batch produced meets the minimum standard for continuous application. So we have a defined concentration that we need to hit every single time for that continuation of application. The AD Pro additive is activated on site, meaning each addition of product is at the highest possible concentration. By activation, what we do is we take the spores, we mix them with a phosphate buffer and water. We raise the temperature to about 45 degrees Celsius and we hold it there for about 45 minutes. And then we inject it into the feedstock as it's being fed into the digester. The AD Pro additive uses a proprietary blend of facultative anaerobes, specifically designed to only affect this stage of the process. And because of that, we're only trying to affect the hydrolysis. So we're not having bacteria that are going to hang around within the system. We affect the hydrolysis, then the bacteria will die off. The addition of AD Pro is hands off for the operator. So the only requirement from the site operation is for the bottles to be changed. And the guys at Amur, that's every 10 days. So the bottles are a 10-day stock. The only other checks that need to be done is a daily check to make sure there's no errors or alarm lights on the unit. We've got our V3 unit coming soon. That's going to have a telemetry system so that we can then see remotely what's happening with the unit, and it'll send us error messages. So we will know probably before the plant know if there are any issues. It only requires basic maintenance. There's only 4 components within the unit itself. They're all interchangeable, plug and play. So we can change units out very quickly. And the installation is very simple. It just needs access to a clean water supply. It needs 110 or 240 volt power supply. Mains power supply is perfectly fine. And it needs a suitable injection point, typically a 1/2 inch to a 3/4 inch fitting that you find on most pumps or on most feed lines. And yeah, just to finish off, AD Pro, it is true bioaugmentation. We are using bacteria to improve the gas yield of the process. And I think that's it from us, isn't it, Chris?
Yeah, I think so. That's fine. Obviously, if any questions, please contact us. And the details, I'm sure, will be shared. Thank you very much.
Thank you for keeping so excellently to time. We've got some questions that have come up in the chat, but I noticed that you've answered them as we've gone along. So just so that everybody's aware, that there is a bit of an extra information in the chat there. So thank you very much. And we now move on to the next talk, which is Optimising Your Microbes, from James Chong at the University of York.
Hi, thanks, Elspeth. Great. If I can have the next slide, please. So, as you've just heard, microbiology is at the center of the AD process. Just to put that in context, London has got about 10 million people, just under at the moment as a population. That's the same number of individuals as you find in 1 milliliter of anaerobic digestion sludge. So there's a huge and complex community offering all sorts of interesting services. And again, you can see here that we know that the AD process occurs in a number of steps. Chris and Matt were just talking about enhancing the hydrolysis step, which is that early stage of breaking large molecules down into smaller molecules that then can be fermented and ultimately produce the biogas that we're interested in particular methane. So if we can have the next slide, please. As an academic group, we're really interested in how well this microbial community can be influenced and controlled. So we're asking the question of whether microbial AD communities change in predictable ways, and if so, how we potentially could drive those changes to help us. You know, are there levers that we can use that will allow us to change the microbial community? And obviously, really what we'd like to be able to do is understand the community well enough that we can model it and make predictions about how potential interventions might change that community and improve the process. And so for that, we're also asking, what do we need to measure? Because a lot of the tools I'm going to talk to you about today are not rapid. And obviously, when you're on site, you want to know when your process is going wrong, why it's going wrong, not in 6 months' time, why it went wrong. Okay, if we can have the next slide, please. So I'm going to talk to you mainly today about DNA-based processes. So we extract, we take a sample from an AD plant and extract the DNA and then use various sequencing methods. And the takeaway message from this slide is just that the microbiology varies. So those colored bars are showing the proportions of different types of microbes within digesters. And here you can see in the top panel, the microbiology in a plant that is fed from a thermal hydrolysis process is quite different to the microbiology that you get from a standard mesophilic system. And in turn, that is also different to the microbiology that's coming in the feed. And we have focused here on sewage sludge. A lot of this work has been done in collaboration with Yorkshire Water. Okay, if we can have the next slide, please, Elspeth. So again, what we've done here in collaboration with Yorkshire Water is we've taken samples from one of their operating plants where they have 4 independent digesters that are all being fed from a single pipe. We've taken samples over about 9 months of time. And what you can see here is a series of panels. Each of these panels is a different microbe in this process. Overall, we reckon there's somewhere between probably 300 and 500 different sorts of organism playing a part in AD. And what you can see in this zoomed in panel is the behavior of just one of these microbes in those 4 digesters. So over this 9-month period, that particular organism is changing as those lines indicate. The 4 different colors are just the 4 different digesters. And you can also see the abundance of that organism in the feedstock. So clearly there's something going on in the digesters that mean that this organism is a different concentration within the digesters to what's going on in the feedstock. But the really nice and important thing here is that, you know, at this scale, which is about 4,000 cubic meters, these digesters are behaving in a reproducible way over long periods of time, which really, for me, the takeaway is that, you know, potentially we can predict what's going on with this microbiology, and we can potentially get a consistent outcome from any interventions we might come up with. Okay, if we can have the next slide. So this is a similar sort of experiment, but now looking at Thames water in particular, looking at what happens when you take a digester or two digesters and switch the feed. So this was carried out at the Basingstoke Wastewater Treatment Works by Thames. They switched their digesters from standard sewage sludge to, again, thermally treated sewage sludge, and sampled over that period as they went through a transition. And hopefully what you can see here is, again, their digesters, the microbes within their digesters are changing in reproducible ways, and they're responding to this change in feedstock. So on the whole, you're seeing some organisms that really don't like being fed thermally hydrolyzed sludge, and they're dying off, so those lines are going down. And you're seeing other organisms that are responding positively to seeing the THP sludge and increasing in number as that transition occurs. And if we go on to the next slide, we can focus in particular on the methane producing organisms. So these live at the bottom of the food chain, and they're producing the methane that we value in biogas. And here you can see there are certain organisms, again, dying off, and others that are replacing them. What's particularly interesting about this is the dogma within the field is that methanosata and methanosarcina tend not to coexist in digesters because they respond to different concentrations of acetic acid. But what we're seeing quite clearly in the data here is that there are methanosatae that are appearing and becoming quite dominant, but they're different species to the ones that were there in the original digester. But at the same time as the methanosatae are appearing, we're also seeing specialized methanosarcina that can cope with the conditions being driven by THP. And you can see this hopefully correlates quite nicely with the other changes that we're seeing within the digester as it goes to THP feed. So for example, ammonia concentrations run at higher levels in a THP fed system. Great. Okay, if we can go to the next slide. So this is just one final example, I guess, of this idea, so that people hopefully believe that this is a very reproducible phenomenon and that there is potential to influence the microbes. So here you're looking at process data. The bottom parts of these panels show methane concentration over time. This was a series of experiments that were actually carried out by the University of Southampton. We facilitated the microbial analysis in collaboration with Sheffield and United Utilities and a number of other companies. So what you can see here is Southampton have taken lab scale digesters now and fed them with different concentrations of carbon in the form of COD, but then they have gradually increased the amount of hydrogen that's being injected into digesters. And what happens is, as you add more hydrogen to these digesters, you get increasing amounts of methane, and you can get up to, so the biogas coming out without any other type of filtering or upgrading is coming out at 90 to 95% methane because the carbon dioxide is being converted into methane through the additional hydrogen that's being added to the digesters. If we go on to the next slide, we can see what happens to the microbiology. So this is a busy and complicated slide. And again, if you just focus on the enlarged panel, what you can see is that Southampton actually ran pairs of digesters, either 2, 3, 4, or 5 grams of carbon per litre per day. And then over time, they increased the hydrogen as well. So these lines actually represent about 14 or 15 months of sampling. And again, we're seeing reproducible reactions by the microbes to their environment, and they're integrating the information of both the amount of carbon they have and the hydrogen that's available in order to change the community and the community dynamics. If we go on to the next slide, again, you can see that the methanogens in this process are changing quite dramatically. So although these are essentially the same classes of methanogen, different individuals are responding to the concentrations of nutrients that they're seeing in the digester. And so there's a very dynamic response in the microbial communities to what they're being fed. So then my last slide just shows potential ways that we can monitor this process in a very rapid way. So we've developed some LAMP assays. So this is the same technology that has been used in some cases for following COVID. You can get a response once you have DNA within about 5 minutes. These are low-cost assays. You can see at the bottom here, you can basically have a colorimetric response to the presence or absence of an organism, but we think this can be further developed so that you can get quantitative information about whether or not the organisms that we may think are key in the AD process are there and functioning as we expect and how they're changing. Okay, so my last slide is just acknowledgements of all the people that have done the work, because it's mainly not me, and the people that we collaborate with. And that's it. Thank you.
Lovely, thanks, James. We've got a question, but I think we'll save it to the end because we're up against the timescales now. So thanks very much, James. And with that, we will go on to the next speaker, which is Will Zimmerman, talking about microbubbles and intensification of anaerobic digestion.
Okay, can you hear me?
Yes, I can hear you.
Excellent. Okay. So when we're saying intensification, we're looking here particularly at gas exchange. And I think we can move on to the next slide because everybody has now seen the title and the collaborators. Okay, so I'm going to give you a brief slide about how we make the microbubbles because it's unique. Everybody else makes microbubbles generally by using a lot of intensive energy and turbulent flow. We inject gas in laminar flow and consequently have a completely different regime. Secondly, how could we use microbubbles to intensify the gas exchange in anaerobic digestion? I've got a slide on that, and particularly using the extraction of ammonia from aqueous solution by microbubble distillation, which is an invention on top of our microbubble generation approach. And then finally, the big reveal, how do microbubbles actually perform using wet food waste anaerobic digestion? And that's at lab bench and pilot plant studies. So next slide, please. Okay, so this is the only non-chemical equation you'll see, which is fluidic oscillator plus microporous diffuser equals microbubbles. Generally, we can tune the frequency of the oscillation and the strength of the pulse appropriate for whatever liquid we're putting in order to create bubbles on the size of the pore. So that's the left side. You can see a fine mist of microbubbles that are around in that size 45 microns on average from 20 micron size pores. We have a paper recently where we've done 7 micron size on average from 2 micron size pores. So you get the idea that we can get on the scale of the pore. On the right-hand side, you'll see steady flow through the same diffuser, nominally the same conditions, and you can actually see very large bubbles. That's why I chose this combination, because it's one of the largest contrasts you can see. Those are golf ball size bubbles, or centimeter size on the left, on the right, and that gives us a sort of 200-fold difference in size with and without oscillation. Next slide, please. Okay, so my guiding principle is the Chateliers Principle, which you all learned in high school chemistry. You can immediately say, oh, but that doesn't apply to biology because they're not equilibrium reactions. But actually, if you think about the effects of removing inhibition or adding inhibition, they actually go in the same direction. So the first equation there is a very simplified overall equation that looks just at what gases we could get on the right-hand side, or vapors. And as you can see, the end source in the organic material on the left-hand side of the reaction leads to ammonia as the common a product of the reaction that is a vapor or a gas at room temperature. And then there's also the desired product, which is methane. And of course, there'll be several other gases that come from the impurities like sulfides and hydrogen sulfide, etc. The final reaction in the transformation that we're all trying to achieve to methane is what the methanogens do. And that takes hydrogen plus carbon dioxide, produces methane and water. So simply with these gases that we can see on the page, there's 4 things we could do based on the Le Chatelier's principle. We could remove methane better, and that's Le Chatelier's pull. We did that and published it with El-Mashadani et al. In 2016 by using pure carbon dioxide microbubbles that were seeded for 5 minutes a day. They were less than 100 microns in size, so generally they would be there for many hours. 20 micron size bubbles would be there, for instance, tomorrow. We could push in more carbon dioxide gas, and that's Le Chatelier's push, providing more food. Elise Cartmel at Cranfield University has done this to the headspace, but not through microbubbles. You could push in more hydrogen, and we just heard about that from the DZ-AD project that included James Chong and several other speakers here. Pushing in more hydrogen achieved 95% biomethane produced rather than the usual 60 to 70%, but that was done again in the headspace, not by microbubbles. And finally, we can remove ammonia by Le Chatelier's pool, and that's been done by my PhD student in conjunction with a spin-out company, Dr. Desai, who's the CEO, as you saw on the front page. Next slide, please. Okay, so how does microbubble distillation work? Very quickly, so let's press a few returns, okay? If we put a hot microbubble in, it's got 2 choices. It can exchange heat with its environment, or it can vaporize volatile gases. So the graph on the left is to demonstrate that on the time scale of milliseconds, we vaporize what's on the interface and achieve the equilibrium at the temperature of this hot bubble. If we let it continue to rise, then the amount of humidity or whatever volatile gas that we vaporized goes from that maximum down back to about equilibrium with the temperature of the liquid. So a hot microbubble can achieve a much higher evaporation, much higher humidification, but can strip volatile gases. Okay, so let's go to the next slide. In the lab, we've implemented this. Please hit a few more carriage returns. So there's a very simple apparatus that was set up. One more carriage return, please, which has the unique features. One, a bespoke diffuser on the right that is supposed to work optimally with oscillation in the flow rather than steady flow, for which every other diffuser has been designed, and the ability to change the liquid level height. Ultimately, we can achieve that millisecond or so of contact time by blasting the microbubbles through, and a liquid layer height of 2 to 5 centimeters. Okay, next slide, please. Right, we've achieved it at the pilot plant by building what we call a distillation column, but this is simply building up vertically to multiply the number of stages. It's still a batch distillation in the terms of the chemical engineering parlance, but you can achieve it vertically and therefore get a higher throughput. And so we've done this at pilot scale. Next slide, please. Okay, so the ammonia removal we've just published on, this is in press, and have achieved an efficiency of 99% removal ammonia in 7 minutes of contact time. The literature is on the right there, and our red dot is where we are relative to stripping, absorption, chemical precipitation, and oxidation in the literature. So substantially faster and substantially higher efficiency, and it can be applied for the range of concentrations of 5 to 5,000 parts per million, generally the levels you get in wastewaters, And you don't need to add alkali. It just takes longer. If we do this at pH, for instance, 7, we get a 35% efficiency. So you'd have to go through three recycles, for instance, to try to get to the 90s of the removal rate. So hot microbubble stripping uses the Chateliers principle to reassociate the ammonium ion and the hydroxide ion. Next slide, please. Okay, so this question of how do we intensify the gas transfer comes from a very simple cartoon, which notices that the conventional theory imagines that all of the metabolites and dissolved gases are going to swim through water from one microorganism to another. If you put the bubble in between, you find there's another possibility that if they're associated on the skin of the microbubble, they can go through the gas phase. And that's 10 to the 4 times faster. And because we can achieve so much surface area, the collisions between microbubbles and particulates, particularly the methanogens, acetogens, and acidogens, is going to exchange hydrogen and collect methane. But those two gases are practically insoluble in water, and they're the bottleneck for gas transfer. So by complexing them, we call this a artificial lichen. The trophism is the driving force. Next slide, please. Okay, so did they actually happen in real life? This is from 50 years ago, a picture on a microscope slide of a fine bubble surrounded by yeast. And you can see there's a fine bubble of air, and they're all attracted because they're oxygen starved. So trophism does attract microorganisms to microbubbles. I've got 4 examples from the literature with larger bubbles than ours. So certainly by dispersing a lot of small bubbles, we are going to have a lot of these collisions and potentially associations. Final slide, please, the big reveal. Okay, so what did we achieve? Up to 13-fold increase in batch wet food waste bioreactions, where conventionally it takes 20 to 25 days for the batch to get all the biogas out. We achieved repeatedly less than 4 days to get all the biogas out using these approaches, less the ammonia stripping, which is still in testing phases at the moment. And our proposed mechanism is the artificial lichen. The in situ ammonia removal, we're going to hear about in the next period as the doctoral student is finishing, with how much more that will accelerate and intensify the gas exchange. Thank you very much.
Lovely, thank you very much, Will. And again, we're up to our time limit, so we'll leave the questions to the end and move on to the next speaker. This is better mixing for better productivity from Jon Bridgeman, the University of Bradford.
Thanks, Elspeth. Good morning, everybody. What I want to do is to give you a very brief overview of something I've been working on with my collaborator, Davide Pello, for several years now. Essentially, we're modelling the anaerobic digestion mixing process to improve productivity in terms of biogas production. And we've been doing that using computational modelling and computational fluid dynamics in particular. Can you move on 2 slides, please, Elspeth? And the next one, that's it. So CFD, computational fluid dynamics, is the computer-based simulation of systems which involve fluid flow and heat transfer. And using CFD, we can simulate steady state, time-dependent, laminar or turbulent flows, multiple phases, solids, liquids, and gas, as we'll see, as well as the concurrent or any concurrent transport processes like heat transfer, mass transfer, and chemical reactions, which interfere with the flow. Next slide, please. And just press return once, that's it, that's great. So over the years, we have been able to model successfully many different types of process in both clean water and dirty water. Next slide, please. But obviously today, what we're interested in is anaerobic digestion of sewage sludge from the wastewater treatment process and the mixing in particular. Next slide, please. So why do we want to mix sludge? Well, in a digester, we want to ensure that we've got maximum contact between microorganisms and food material to ensure that we get as much digestion of the organics as possible to produce the methane-rich biogas, which we can then use as an energy source. And so we want to maximize energy recovery. Obviously, we also want to ensure that when sludge is treated and withdrawn from the digester, it's sufficiently stabilised in accordance with legislation. And we want to ensure that as little grit as possible and debris accumulates in the digester, because that reduces the overall working volume, reduces the hydraulic retention time, and so reduces the performance efficiency and the biogas production. Next slide, please. We know that mixing is an energy-intensive process. We also know that until now, design practice has been rooted really in rule of thumb and empiricism rather than science. And I think it's fair to say that the focus of designers has principally been on treated sludge quality, and the topic of energy recovery has been of secondary performance. And if you cast your mind back to when Jon Brigg was talking earlier, he said something similar, that the focus of digestion has been on stabilisation. What our work has been trying to do, we've been trying to answer a question that, is it possible to decrease the amount of energy that we put into to mixing without compromising the biogas production, and indeed possibly increasing the biogas production? Next slide, please. Well, as we all know, sludge is complex. It's a complex liquid, and so that makes it a complex liquid to model. We've got a liquid phase, but we've also got a solid phase, but that solid phase varies depending upon the digestion process. Sludge doesn't behave like a normal fluid. Its viscosity changes under different conditions, and so we have to take that into account when we're modelling it as well. We have sedimentation issues, which we want to avoid. And of course, if we're modelling a gas mixed digester, we have that additional gas phase as well. Next slide, please. So I started this work getting on for 10 years ago. So we're now involved in a long-term project to assess digester mixing efficiency and design, and the link with biogas yield. We started very basically looking at a mechanically mixed 6-litre lab scale vessel. And our overall aim was to assess the hydraulic performance of that digester under different sludge loading criteria. You just click return. So that's the mesh that we had. And then next slide, please. And so what we were able to produce, we model various different dissolved solids concentrations, and you can see that as the dissolved solids concentration increases, there's a significant decrease in the movement of the sludge in the vessel, and we found it was actually a very poor vessel for mixing. Next slide, please. But safe in the knowledge that we could model this non-Newtonian sewage sludge, we turned our attention to gas rather than mechanical mixing. Next slide, please. And we considered a traditional unconfined gas mixing model. And next slide. But we did start very simply from very basic premise. We started with a simple cylinder into which we injected a gas plume through the base. Next slide, please. We modelled this and we used an optical technique called particle image velocimetry to validate our results. And we got some good agreement between the physical data, which you see on the left-hand side, and the model data, which you see on the right. If I'm honest, we slightly overestimated the velocity in the upper part of the tank and slightly underestimated in the lower part, but by and large, we got good qualitative and quantitative comparison. Next slide, please. This is where it got exciting, because now we've turned our attention to a full-scale plant, which we modelled as a cylinder over an inverted cone, 15 metres high and just over that in diameter. We made some assumptions regarding the symmetry of the vessel, and so we just modelled a slice of it. Next slide, please. If you click on the blue section, please, Elspeth, we hopefully see some flow patterns. Oh no, so go back, please. If you just, that's it, click on that. There you can see the velocity being, the movement of the sludge being induced as a result of the bubbles coming up. And if you click on the other wedge, please. No, back. That's the viscosity changing, because if you remember, I said the viscosity changes within the sludge depending upon the shear. Next slide, please. If we look at these patterns in a bit more detail, what we found was that the flow patterns, the general structure of the patterns was similar for all runs, irrespective of the dry solids concentration that we had. So you've got bubbles forming a column of fast rising liquid. So the bubbles are causing the liquid to move quickly above the nozzle. It reaches the surface of the digester and the liquid is displaced horizontally towards the outer wall, and you can see it then forms a large vortex occupying most of the rest of the digester, with the center of the vortex midway in the upper part of the domain. Inside the vortex, or once in the vortex, the liquid slowly drops down along the outer wall and follows the slope of the digester, returning back to the nozzle. Next slide, please. We also looked in detail at the viscosity of the sludge, and this figure on the right shows that the viscosity drops along the vertical column, and perhaps more interestingly, along the descending branch of the vortex as well. This is due to the fact that sludge is a pseudoplastic fluid. Its viscosity decreases when the shear rate increases. As a result, what we find is flow patterns in which the viscosity is considerably lower than in other areas in the digester. What we know is that areas of flow with a lower viscosity, they will offer less resistance against any incoming liquid, any incoming sludge. And so circulation will be enhanced within the low viscosity areas, but it will also be less effective in the higher viscosity areas. And so that's going to have a detrimental impact on mixing in the digester. Next slide, please. We thought about ways in which we could improve the mixing by breaking the viscosity patterns, and one of the ideas we came up with was to install an additional manifold, which you can see on the figure there. That additional manifold is at a different distance from the centre with additional nozzles. And what we did was we switched the gas injection between the two different manifolds every minute or every 5 minutes in order to try and break the viscosity patterns. I'll spare you the details of how we assess this, how we assess this, but what we found is that we were able to break those viscosity patterns, and we found a definite improvement in performance. Next slide, please. And so what you've got here is on the top, no switching, so you've got the vortex and the viscosity corridors, and on the bottom we've got the results from when we switch the mixing every minute, and you can see that we have disrupted the viscosity, and we no longer have those corridors of low viscosity, and so we were able to demonstrate an improvement in the mixing efficiency. Next slide, please. And so just to summarize, what we found is that the traditional way of mixing in the sites that we've looked at has been largely unsatisfactory. We've got lots of dead zones, unmixed areas. We did find that, you know, if you retrofit the additional manifold, that should produce, our models tell us that should produce an improvement in performance, and we've varied the times for mixing. We found that shorter switching intervals were more effective, but obviously more intensive. And my final slide, please. This has been a labour of love for me over a number of years now, but we are now at the stage where we know that we can model the flow patterns. What we're doing now is the really exciting bit, I think, is we're coupling this with a variant of ADM1, so that now we can tweak the way in which the amount of energy we use for mixing, and we can predict the amount of gas or the changes in gas production that we will get off the digester, so that we can truly optimize the process that we've got. And we are incorporating, as a secondary effect, sedimentation effects as well. So I'll finish there. My contact details are on the screen. I am actually moving to the University of Liverpool in just after Easter, but either of those email addresses currently work if anybody wants to contact me about it. Thank you very much. Back to you, Elspeth.
Lovely, thanks, John. And we've got a question, but again, I think because of the time, we'll leave it for the Q&A at the end. So we now have Ciaran Sharpe from BACB Renewables talking about biomethane upgrading.
Hi, Elspeth. Yes, my name is Ciaran Sharpe. I'm the Business Development Director at BACB Renewables. I'm just going to go through a little bit about our company and the involvement we've had in taking biogas from ADs and landfill sites and upgrading that biogas to biomethane to be used in different formats. Next slide, please. So just a very quick introduction to BACB Renewables. We are a B2B holistic decarbonization consultancy and developer. And we primarily work with clients to decarbonize their operations. On the right-hand side are all the areas that we work in. We have a multidisciplinary team spanning a suite of technologies, again, all on the right-hand side, from solar all the way to anaerobic digestion. And we've been heavily involved in the biogas upgrading market since 2020. And with the introduction of the Green Gas Scheme, which opened in November 2021, our increase and interest from other customers in the biomethane market has grown massively. Next slide, Elspeth. So why is biomethane becoming important and popular out there at the moment in time? Well, pretty simply, supplies of fossil fuels, if you've seen anything on the news, of course, I don't want to go into that, but lots of countries in the world do not have their own supply of natural resources in terms of fossil fuels, so are reliant on other countries. And as you've seen, I'm sure at the petrol pumps, fuel prices have shot over the issues abroad, as well as gas prices for heating and electricity have skyrocketed. Just to give an idea of it, about 2 years ago, roughly most of our clients residential were on 15 pence to 16 pence per kilowatt. That shot up to about 30 now in a very short period of time. That doesn't seem like it's to be dropping. So there's a big push to phase out fossil fuels, and potentially at the end of the day, they're becoming harder to find. They're getting more expensive and dangerous to collect. And at some point they will run out. So we have to try and find renewable alternatives, and a fantastic renewable alternative for natural gas is biomethane, because molecularly it's the same thing. Biomethane will contribute to decarbonizing the gas network for sure, and greening the gas grid is what it will do. Biomethane is also becoming more important because not only is it good to be injected into the grid to phase out natural gas, but most people probably don't realize that some petrol stations offer CNG to be used in fuel source for cars or trucks. And biomethane is making a big push into the road transport fuel sector. You might have seen trucks going down the road, Home Bargains, Waitrose, Morrisons, with symbols on the side saying running off CNG, biomethane, 100% renewable. And the reason they're moving into that market is, one, because of RTFO credits, renewable transport fuel obligation credits. And in essence, what they are, and is driving this push, is companies like Morrisons, like Waitrose, like Home Bargains have to decarbonize. And put it simply, the only way they can decarbonize is to invest in renewables. Well, with these RTFO credits, they are able to purchase these from people who are producing biomethane. One, biomethane is cheaper than running off diesel. And two, they're able to use the credits to offset their carbon emissions. And of course, for people out there producing biomethane, they are able to sell those credits onto big customers. So there's a very lucrative business out there at this moment in time in the biomethane market. Next slide, please. So our biogas upgrading process is a little bit different to what is out there in the market, which is membrane technology, which is a high energy form of upgrading biogas to biomethane. Our process and our partner that we work with, we use a PSA, or pressure swing adsorption, which provides a very simple biogas upgrading process. So in essence, I'm just going to run you through the process and how it works. So the biogas enters the system. It is compressed. It is then cleaned of hydrogen sulfide and other trace gases using activated carbon. It is then moved to a next section, which it is cooled to remove as much water as possible from the gas. The biogas is then passed through an adsorber filled with a carbon molecule sleeve in which the carbon dioxide and other contaminants in the gas, such as ammonia, nitrogen, oxygen, are removed prior to the gas moving off to become biomethane. And in order to make this process continuous, which the system is, production is then moved to a second PSA after a predetermined interval, depending on the quality of the entering gas. This allows the first PSA to be fully vacuum regenerated, and the system continues as is. And again, like I said, this can then be moved off into a system to either compress or liquefy the gas to be used in the road transport, or to be moved to a grid injection point. Or if you're close enough to a grid injection point, it can just be injected straight into the system. Next slide, please. So the company we work with solely on this is a company called Carbotech. They've been in the business since 1989, and they are a German company based out in Essen. And we spent a long time working with these people and finding out that the technology was sensible for the UK, and particularly with everything that's happened, has made it definitely a very competitive product to bring into the market for biogas increase, as well as the demand now for biogas, because right now in this market, biomethane is in high demand, but the supply isn't meeting that demand. So hence why lots of people are moving towards AD and finding ways of upgrading biogas to be used either in the gas network or in road transport. So some of the benefits that Carbo bring to the table, all the gas we take, we analyze and custom build every single Carbotech system for our clients. So there is no off-the-shelf solution. Everything is customized because everyone's gas will be different. It is pre-assembled and it is tested to make sure the quality of the biomethane in the system works to the levels that we guarantee and promise before it is delivered on site. So that when it is assembled on site, it is already tested prior to being delivered. A big thing for Carbotech, it is the lowest electrical power requirement system for biogas upgrading to biomethane in the market, which quite simply means with electricity prices going through the roof and no sight in the future for them to drop anytime soon, it is a great way to find out that this is more profitable for our customers in this market. One of the other benefits to the Carbotech system is that we're able to take unusable tail gas from the system and run it through a generator to lessen the electrical demand on the grid, and to again increase the profitability, utilizing everything that's possible from the system. So if it can't be used for biomethane, it can be run through the tail gas to power a generator. It is a high methane recovery. It is also a dry process, which means there's no requirement for water or to deal with wastewater from the system, which again means it's more profitable for the client in producing biomethane, but also making it an absolute dream to put through planning. There is no thermal power requirement. Again, more profitability, less requirement for power outside. And another thing for planning is there is no toxic chemicals involved in the process. And that is everything, Elspeth. The next slide, please. Thank you for listening to me.
Lovely. Thank you very much, Ciaran. We'll now move on to final talk, which is from Nick Humphries on N2 Applied, talking about reducing emissions from digestate.
Great, thank you, Elspeth, and morning all. So yeah, I'm Nick Humphries, I'm Chief Agronomist for N2 Applied. So N2 Applied is a Norwegian ag tech company who developed a treatment method for slurries and digestates. If you go next slide, please. So what the technology is, it's a two-stage process. First stage, we have a plasma torch, essentially, which is breaking apart nitrogen and oxygen in the air. And then we're creating that reactive nitrogen gas, which is fed into the digestate or the slurry. And that stabilizes the digestate. So what we're doing is we're adding more nitrogen as a fertilizer source by adding this nitrogen gas in. We are acidifying, so it's an acidification method. So it's locking on all the ammonia emissions, which we usually get. It also stabilizes any excess methane emissions. So we do still have some in digestate, especially in slurry as well. That carbon can break down into the methane. By lowering the pH and adding in nitrates, we're inhibiting that. And also the odours reduced as well. So especially in livestock production, that's a big benefit. It is a plasma unit at the moment. It's containerized system. The way we've designed it was to sort of point towards a small dairy farm at the moment, but it's a scalable technology. So the current units are 50 kilowatt units, treat slurry from about 200 cows, probably about 3,000 cube of digestate a year, but it can be scaled up to plant size, and that's kind of the direction we'll look into in the future. Next slide, please, Aswad. So the technology's been developed over about 10, nearly 11 years now. Quite a lot of investment gone in, £21.5 million so far. And we've got quite a broad team. We've got engineers working on the development of the units, agronomists like myself working on how to implement this on the field and get the best fertilizer response. And we've got the plasma engineers, nuclear scientists almost, optimising the energy input. And the current Mark 4.5 plasma units is what's going commercial this year. So we do have them rolling out. In the UK, we have 3 of the Mark 4.4 machines on farms. They've been operating for about a year now. And the Mark 4.5 is the next commercial stage launching. As I mentioned, we'll be looking towards more bespoke solutions for the bigger farms and maybe for AD plants as well, where the capacity is a lot higher. And we might just need to, economy of scale to service that. Next slide, please. So what the actual digestate looks like once it's treated. So beforehand, we have an organic nitrogen and a ammonium nitrogen content. But that ammonium nitrogen is really unstable. We can lose 30 to 70%, sometimes maybe more, as ammonia gas. So that's air quality issues, but it's also a fertilizer loss. It makes the digestate less effective when it's applied to field. We are stabilizing that ammonium, so that stays in the liquid for when it goes onto field. It's then crop available, could be taken up by the soil, by the crop, and we're not losing it to the wider atmosphere. We're also adding in nitrates and nitrites. So the nitrates around the same proportion as the ammonium content. That's there as, again, effective fertilizer. It's crop available. And then the nitrites is part of the absorption process as well. That actually helps stabilize the liquid. That's what's preventing a lot of the methane production, inhibiting a lot of the microbes. It's still microbially active when it goes to soil, or the organic nitrogen is still there, or the organic carbon, which would still be in there, is the P, the K, everything else, it's not touched. We preserve that, and we're adding in this extra amount of nitrogen as a fertilizer source. Next slide, please. So we've worked hard to evidence this over several years. We have about 5 years worth of field trials now, and we've been doing a lot of storage trials and emissions trials with the independent institutions. So this was one done on digestate with RISE, so Research Institute Sweden. And what we saw is over 95% reduction in ammonia loss in store, and 99.9% reduction in the methane loss as well. So I'll say this is a digestate as well, so we can see there is the methane loss in slurry, it's even higher. And then that translates over to a direct carbon reduction for carbon footprints. Yes, and this is a storage solution as well. So we are in storage and on field application. Once it's stable, and we're sort of an alternative to multiple technologies then. So in some cases, you might not need to cover your stores because we've stabilized, and we have open stores. We've got one up in Scotland, an open tower store, which is open to the elements, and it stays stable all through the winter to be applied in the spring. So it is a stable solution, and we've got ways to maintain that as well as part of the infrastructure. And next slide, please. And so your field application as well. We worked with ADAS. So this is 2020 trial. We've done 2021 as well. But this was on digestate, a dairy digestate from dairy farm, small digester feeding biomass and dairy slurry. And what we saw was quite a high loss of the ammonia on field, and this was band spread. So this is the recommended method for reducing, and not as straight as injection, but band spreading is a low emissions technology. And we saw we lost around 45% of the nitrogen applied. It was a warm day, but wasn't particularly bad day for spreading. It was a day you want to spread in the spring, and we saw a lot of that end lost. Whereas in the Neo, we managed to maintain quite a low level of emissions. So it was about an 80% reduction in this, but in terms of actual nitrogen applied, it was, we saw what we needed to go to the crop was there. We had an even better trial this year on slurry, or last year, sorry, where we had an ammonium nitrate as a baseline as well, and we saw 2% loss from the NEO compared to 21% loss from the untreated, but only 2% loss from the AN as well. So we actually matched the ammonium nitrate. So as a chemical fertilizer, essentially what we're seeing from ammonia loss is what the background levels are from the soil anyway, if you apply any nitrogen. So we are really stabilizing that ammonia loss, and it's yeah, on the field application and in storage, as I say. Next slide, please. So this was the same trial with ADAS, and we did nitrogen use efficiency to see the crop effect. And as you can see there, we had a much higher yield response from the plasma treated digestates compared to the untreated, but also it was comparable to the top end of the nitrogen response curve with ammonium nitrates, which we did. So it translated over, there was a 63% nitrogen use efficiency of the ammonium nitrates, which is something you'd expect. So the crop was yielding from that. We were at 61%, so very, very close. The untreated digestate was at 28%, so less than half. So we are getting the yield response of an ammonium nitrate fertilizer, and we've seen this time and time again now in trials. We had a really good trial with OAT Oxford Ag trials in Goole this year, or last year, sorry. We saw again a really high response, and actually on those soils we saw a better response than ammonium nitrate because we still had the organic nitrogen as well, which was feeding the crop in the long term. And we'll continue to do this to validate the fertilizer response. Next slide, please. And then, yes, this is just a summary of all our trials over the last, this is 2 years, so 2020, 2021, where we've run quite a number of trials, and we've seen on average over an untreated substrate, it's about a 38 to 40% increase in yield from the same nitrogen application in terms of total nitrogen. So we're seeing time and time again that increase in yield, depending on the soil type and the crop type, but it's consistently there. And next slide, please. And so, yes, this is a piece of work we did with BDC. So this was ADSI, which was mentioned at the start. We did locally. We did dewatering. Sorry for the not very attractive slide. I didn't have time to visualize it properly. But the main takeaway here was we often get the question about dewatering from AD, how we can help with that process. So what we saw from this was all the nitrogen that we added as nitrate was being preserved through evaporation in vacuum ovens. We did see still ammonium loss, but we think we're going to stabilize more of that. So this was kind of an initial experiment where we wanted to just see what happened when we dewatered. As I say, all the nitrogen we're adding is being preserved, so you've got a higher value sort of cake or pellets. I'd probably say cake's the best way to go, just for stability. But we think we can also maintain that ammonium because we're inhibiting the loss of it. So recycling heat to evaporation, we can also recycle 70% of the energy which goes into this process as heat exchange. So then there's probably quite a nice balance there with the right partner, engineering partner, where we can use evaporation, preserve all the ammonium, the nitrates and everything else, get to a really high value cake for transport or further on. But yeah, it's exciting results initially. And thanks again to BDC and Alessi for arranging this piece of work. Next slide, please. And yes, so just on the final stage, we did some calculations based on IPCC figures to try and show what the reduction in carbon footprint would be. With a Mark 4.5 unit, which was, I say, probably around 2,500 to 3,000 cube of slurry of digestate, we would look at about 108 tons reduction of carbon from that volume with our unit. So this is per unit. Most of that comes from the fertilizer replacements in this case. There's a lot coming from the methane reduction as well. We're at 44 tons in this case. If we were looking at this in terms of a slurry, it would be about 3 times that because they've got a lot more carbon. But yeah, this is the unit, and as I say, it's scalable for the AD process, and this will change, but it's a good indication. Next slide, please. So yeah, that's me. As I say, we've had a lot of independent validation of this work. You can see a trial map there of the field trials we've done. Our main office is in Norway, but we do a lot of work with universities as well to validate everything we're doing, and continue to look to expand around Europe. Thank you very much.
Lovely, thank you, Nick. Impressive potential to impact on decarbonisation of agriculture there. So we're going to take the questions now. I'm going to start at the back because we've got a question for Nick, so we might as well do that one first. But if I could ask all the other speakers just to make sure they're unmuted so that I can ask them questions as well. So Nick, what impact has O3O and other radicals from the plasma process on the digestate?
Yeah, so we see there are some free radicals in there. It's similar to what the nitrate and the pH lowering is doing. It's inhibiting the microbial activity. So say that's probably one of the control factors on the methane side. We don't have a lot of exhaust gases on this, so the absorption system is really tailored to be as efficient as possible. So we're not worried about any of those, any gases coming off, but in the liquid itself, it's stabilizing the microbial activity. To test that doesn't impact the soil negatively, we did work with Cranfield last year, actually looking at microbial biomass, microbial diversity in the soil, and there was no negative impact. So it's concentrated in the digestate, but even when you apply it at quite high rates to the soil, it's more of the nutrient response than anything. There's no problems with damaging the soil microbiome.
Lovely, thank you. I've got a question for Jon Brigg as well. What's the potential of innovation to tackle pollution from AD, such as pollution from digestate? You'll need to unmute yourself, Jon.
I think you need to unmute by the looks of it.
Yeah, we're trying to do that.
You've unmuted Jon Bridgeman, and you should have unmuted Jon Brigg.
All right.
There you go. That's it. Often confuse me and Jon Bridgeman. Yeah. So we've just had a great presentation from Nick there about how that can be achieved. So I think this is one of the knowledge of. So we'll come back to the business proposition for stabilizing digestates. Is twofold. One is the value of the nutrients that are being lost. You've seen there the volatilization of ammonia there from both tank storage and in spreading itself. That's a lost resource which is worth money. So that's the first thing. Secondly is the understanding of the carbon impact of that volatilization is now becoming much more largely understood. So the carbon implications of applying manures in a liquid format especially, but post-digestate where there's still quite a lot of potentially ammonia and of course methane still in there, which both have pollutive effects, is going to be substantial. So there's going to be a negative impact on the carbon accounting of agriculture, of industrial applications of AD digestate management, as well as water companies. So there's two imperatives there to do this, and it's great to see technologies like Nick promoting there coming through to help stabilize that. I think there's much greater potential. So what if you look at the impacts of cost of fertilizer in the current climate coming from the east, that is a real red flag warning now for so there's supply chain impact and cost impact, price rises coming left, right and center from pretty much every angle. So the imperative is absolutely there. So this kind of incremental investment, if you like, in stabilizing nutrients and therefore reducing carbon emissions is absolutely critical.
Okay, thank you. I've got a question for Laura.
Yeah.
So Laura, your plant is in Spain. Could the warm climate have affected your results?
Not really. When we've done BMP testing, for example, there's no, say, impact on those lab test results from the climate. And we've seen those increases that we were speaking about, not just in the industrial scale operation. And I think there was a question sort of the same or related earlier on in the chat. There's no real impact on our unit regarding climate unless you set up the Biomark somewhere in the north of Canada. It'd just be related to installation, really. Results per se, I mean, cost per se would not be affected. It depends mostly on the type of feedstock, stuff like moisture. The more moist that the feedstock is, the higher the the thermal demand to bring it up to temperature and pressure. But results wise, we haven't really seen that climate in Spain or UK has an impact on either making them more positive or negative, really.
Thank you, Laura. And now I've got a question for Matt and Chris from NCH and Amur. How long does a unit last?
Matt, do you want to answer that one?
Yeah, the units themselves, the supply that we're doing is a rental basis, so it's all fully maintained. But the units themselves should last indefinitely with basic maintenance. We do get some issues, and we have tested a few to destruction on the plant at Amur. So we know, the conditions that we need now in terms of the environment that we need and what have you. But yeah, it's one of those. It's put it in, and it will last as long as it lasts. To be honest, you're not paying for it. You're paying a rental fee, and you're paying for the spores at the same point.
Lovely, thank you. Right, I've got questions for James next. Would you predict that seasonal variation in microbe competition is due to environmental factors or differences in the feedstock, such as seasonal variation in diet?
Yeah, so I think probably feedstock is going to be the biggest driver. Obviously, things like environmental conditions, if the temperature drops externally and your digester isn't very well insulated, or your heat exchanger isn't able to maintain the temperature, that is going to have an effect, but I would imagine that largely, you are what you eat is actually the case. So feedstock variation is probably what's driving things the most.
And also, do you have any thoughts on how the microbes might interact with the probiotic additives that we heard about in the previous talk?
No, and that's really interesting. It would be very interesting to see how that additive affects the community. From what Chris and Matt was saying, it should only affect one part of the process, but it would be very interesting to see what the knock-on effects were to the rest of the community.
So for Will Zimmerman, do you know whether this lichen effect works for AD microbes?
Do we know if it works for AD microbes? Let's say at the moment we're just trying to puzzle out how you can achieve several orders of magnitude faster production of gas without having several orders of magnitude greater transfer of hydrogen. It's the limitation is that hydrogen, the methanogens are hydrogen starved, hydrogen doesn't swim, so it has to go from the acetogens and acidogens to the methanogens. So we don't have any visual evidence of that, largely because of results, and secondly, because the scenario is opaque, that all that biomass in there makes it quite difficult to visualize what's happening. We do have another system, however, where we put microalgae and yeast into landfill leachate that had the ammonia removed, and those we have visualized the complexes, and also we've used microbubbles to differentially float and separate yeast from microalgae. So we can achieve the complex, or we can achieve by tuning what the content of the bubble is and the additives, whether you tracked the microalgae preferentially to the bubble or the yeast preferentially to the bubble in the mixture, or both at the same time. So we have evidence of it in other systems, but anaerobic digestion with all of that biomass is quite difficult to see because it's opaque.
Thank you. I've got another question for you. Has the microbubble ammonia stripping been tested at large scale? And does the air injection impact the biogas production? Okay.
First, we've used a number of different gases to strip with, and it's not clear whether or not we'll strip with nitrogen or CO2. as the stripping gas for the hot microbubbles. Air we have used with a number of different scenarios including anaerobic digestion centrate. Does it affect the biogas removal? It really depends on how you stage it. And at the moment we stage it by taking samples off of the anaerobic digester, strip the ammonia, and then return the sample. And we're hoping to make that a continuous sidearm so that the side unit is the distiller rather than it's being done exactly in the anaerobic digester.
Thank you. Jon, Bridgeman, this time, you've had a couple of questions in the chat that you answered about the injection switching. Is there anything you'd like to say generally to the whole group about that, or?
Yeah, so yeah, the question was around have we looked at any other gas injection scenarios, and the answer is no, not yet. Because what we wanted to do was first of all work out if we could model the movement of the non-Newtonian sludge within the digester. Could we add in the gas phase, which we've now done. The next bit that we're very much focused on is the coupling of the biokinetic model with the hydrodynamic model, so that we can actually predict gas production changes depending upon energy inputs. But the question was, is a fair one. The overall object of the project is to minimise the amount of energy that we input and to maximise the amount of biogas that we get off. And so you're quite right, we do need to look at different injection scenarios to see if they are any more effective than just central and vertical. The other question I was asked was about the reduction in energy usage. Off the top of my head, it was about 50%, but I just need to go back and look at the paper to confirm that. So I prefer you not to quote me on that for the time being, but I will come back with a definitive figure once I've looked at the paper. Thank you.
Thank you. Ciaran, what a question is your system in use in the UK yet?
Yes, it is. Yes, it's at 2 sites at the minute. We predominantly started working with Econward Tech because they were having issues bringing it into the UK. So that's where we've sort of helped them in that side of it to introduce them into the UK. But yes, there is 2 active sites in the UK, one in England and one in Scotland.
Well, when you get one in Yorkshire, you have to let us know and we'll do an AD site visit there.
100%, that's the deal.
Okay. So I'll just share my screen again to let you know what's going to happen next. So thanks very much to speakers, particularly for keeping time so well. The webinar has been recorded and all the delegates will be sent a link to the recording in the next few days. We'll also make a PDF of the slides and you'll be able to access them from the members bit of the BioVal website. So I think most of you are now AD-SIG members, so keep an eye on our newsletter, and we send out an email maybe 3 times a year with different opportunities. And also just say that this is my last AD-SIG event, and that my colleague Caroline Wilcock is going to be taking over. So thank you very much, everybody. Thank you for a great webinar.
Thank you.
Thank you.
Bye, everyone.
Bye.
Everyone.
Thanks. Bye.